try my best to keep on time. If I'm getting close to where you want me to stop, let me know and I'll summarize.
Sure.
Firstly, I'd like to thank the AFMS for giving me this invite to come and present a seminar on the work we've been doing at the University of Queensland Center for Hypersonics, particularly around supersonic combustion and in trying to understand what combustion modes occur in scramjet combustors. My name is Anand Veeraragavan. I'm the co-director for the Center for Hypersonics at UQ. The other co-director is Vince Wheatley, who does a lot of work simulating the kind of experiments that I undertake. You can see there on the bottom a photograph of some of the group members when we had visitors from France. This was a fairly old photo at this point now, but you can gauge the size of the group somewhat from that image there that, we are a group of about 50 people or 60 people in total, accounting for all the academic staff, research staff, technicians, and students. So the work I'm going to show you today is mostly motivated by what I have been doing for the last 13 years at UQ, but by no stretch of imagination is it just my work. Pretty much collaborate across the board with all the group members and even externally with some of our collaborators in achieving the work we do here. Particularly the experiments are very difficult experiments to do, as you will see and appreciate in a few moments when I present the kind of work we do. And therefore, it needs more than one person or a few people doing it. So therefore, we collaborate quite broadly. So I will be representing work that's mine, but also other people's. Now, in terms of what we do here, the graphic on the top left shows you different trajectories. I'll first get the simple thing out of the way, which is our airliners, which everybody is comfortable and familiar with. These are the planes we take to travel and the kind of engine technology that goes in propelling those aircrafts. And then anything else you see on this graph on an altitude and speed sort of regime is got to need something that flies much faster. So this can be something that's like the red curve here, which is a hypersonic space plane that can be used for access to space, or something that as a cruise vehicle, or any other trajectory that you see here will all potentially require something that flies under supersonic or hypersonic speeds. And that's the area of research we're interested in providing opportunities to propel these kinds of vehicles. Now, on the bottom, you see here, there are two engines embedded, and I won't detail what they are here because I'm going to talk to the one that's on the bottom in quite some detail in this talk. But I'll draw your attention to the graphic on the right bottom, which is looking at a performance metric called specific impulse, ISP for short, which is nothing but the thrust that an engine might produce over the fuel flow rate of propellant. And as you can gauge from that terminology, this is more sort of a rocket performance metric that is applied across the board to assess different engines. So rockets on this metric are the lowest common denominator. They don't use any oxygen from the atmosphere. They carry everything. They carry the propellant, which means they carry the oxygen as well as or oxidizer broadly, as well as the fuel that they burn. If you look at any of the other engines that are shown in this plot, which is the turbojets, ramjets, and scramjets, all of these will consume oxygen from the atmosphere. They're called air-breathing engines for that reason. And depending on the type of fuel you use, whether it's hydrogen or hydrocarbon, we can see the performance metric at different speed regimes. One thing to note is no one technology can span, except for rockets, no one technology can span all of the speeds. At lower speeds, turbojet work well. At slightly higher speeds, supersonic speeds, ramjet take over. And then at scramjet speeds, which are about Mach 5 and above, hypersonic speeds, scramjets are the best technology in terms of the performance. And the other engines cannot perform because of underlying physics that prevents them from being operational in those speeds. There will be some overlap, but they cannot extend to the full extent. Now, in this metric, you can see hydrogen-fueled high-speed engines have the best performance. However, I will draw your attention to this image, which I didn't really want to talk about in detail in this graphic. But if you see here, the whole vehicle is airframe integrated. All the engine and the body of the vehicle are all one and the same. Unlike commercial aircrafts, where you have a wing and you have the nacelle of the engine hanging off the wing, when you go to very high speeds, particularly hypersonic speeds, that is not possible because of the frictional drag that will be encountered. It is a necessity that we have to airframe integrate, and everything has to be sleek and has the minimum drag profile. Now, with that constraint, the main constraint we face in terms of realizing such engines is a volume constraint. So if you look at this performance metric and think that we now have a volume constraint and rearrange how we present it, we can think of a similar metric called density impulse. which we defined, which is now thrust per unit volume rate of fuel consumed, not mass flow rate. And on this metric, just showing some properties of the different fuels we might use, normalized by hydrogen, which is the small diamonds. You can see hydrogen is very good in terms of energy released or energy stored per unit mass, but not so good per unit volume. So in this metric now, hydrocarbon fueled engines, scramjet engines, will probably be a better performing vehicle than one that's fueled by hydrogen if you're looking for long duration performance. So keeping that in mind, in today's talk, and I'll talk about all of this, but in today's talk, I'm going to focus pretty much on hydrocarbons fueled engines, but in the context of the history of the work and how we arrived at what we're doing now, I will talk a little bit about some of the hydrogen fuel combustion works we've been doing. Now, to do any of this work in a systematic, considered manner so that it leads to a useful outcome, which can be applied in a future design of some vehicle, and for which we have a case study here in Brisbane by means of a company that's trying to commercialize this technology. We first need facilities that can explore supersonic combustion as a phenomena and such that it matches these conditions that you expect to fly in. It also has to have the ability to explore subsystems. So many a times it won't just be a full vehicle you're testing. You'll probably look at how the fuel injection happens, how the combustor works, and so on and so forth. So for all of that, you need the ability to design experiments and can go into such facilities. And finally, of course, you also need the ability to test the full vehicle or the full engine so that you can ascertain its performance under its operating conditions. Now, the applications multifold, reusable launch vehicles, which is one of the applications that Hypersonics with an X launch systems is commercializing in Brisbane. There's also lowering the cost of such high-speed vehicles. That's a consideration, and potential defense applications. Now, I've talked a lot about scramjet combustors, and I am going to talk to you a whole lot about supersonic combustion modes in scramjets. But before we get into all that, the first thing I want to sort of educate everyone on, if you're not very familiar with these engines, is what is a scramjet engine? What are we talking about here when I say supersonic combustion inside a scramjet engine? So like I said, the whole engine is going to be airframe integrated. That's a schematic shown here. And this is a fun exercise I do when we have visitors visiting our labs and want to look at our models. Many times we have politicians even coming through to have a look at what is the Center for Hypersonics up to. And what we do there is we put some display models, which will potentially have one of these sort of scramjet combustors. And I ask them to go ahead and look inside that combustor to see what it looks like. And inevitably, they look inside and come back up with a puzzled expression. It's empty. It's hollow. It is hollow. That is the key operational aspect of these combustors. It's flying at supersonic or hypersonic speeds. When you fly at hypersonic speeds, shock waves form at the front end of the vehicle. And those shock waves, as air flows through, the shock wave compresses the air to a high pressure. And if you can design your flow path such that you achieve a reasonable amount of compression that you're seeking, you can actually provide compressed high pressure, high temperature air into the combustor region. So that means if you compare it to a jet engine where you need a compressor to compress the ambient air because the air is not rushing into the engine at those speeds, you don't need that compressor in a scramjet vehicle because you don't need a compressor. You don't also need a turbine to power that compressor. So we don't have any of those turbo machinery elements that you would see in a commercial vehicle that's flying at lower speeds. So it's entirely fluid mechanics driven. So in some ways, for the Australasian Fluid Mechanics Society's context, this is a complete fluid mechanics driven vehicle in its truest sense. Okay, so how else does it operate? So first, some compression happens here from the leading edge of the four-body shock. Flow goes through. There's a series of shocks called a shock train that gets established inside here in the isolated region that further compresses the flow, and then we inject the fuel. We have to mix the fuel, achieve ignition in some way, whether it's auto ignition or you have some kind of a forced ignition system, depends on the context. And then we have combustion, which needs to be achieved within a very rapid duration inside of the combustor, produce the extra energy from the chemical fuel that we've injected, and then expand that in the nozzle, providing thrust. So that's the operational physics underlying here. So what are the different bits and pieces and how do we fit into the picture? So at UQ, and I've been rationalizing all the work we do in the shock tunnels in terms of experiments and trying to fit it onto this is what we were starting to study and where are we and what are we doing. So I'll give you a brief snapshot of that here. So firstly, on the four-body side, If you bear in and zoom in, this might be a leading edge that's quite sharp, but over a period of time as it flies, it can degrade and become blunt. So if you have a blunt leading edge, there'll be a shock that's not quite attached to the leading edge. That's shown here. What happens behind that, particularly if you're flying at low trajectories in that map I showed you earlier of all the potential trajectories you can have, you can encounter a scenario where your vehicle is compressing the flow here in that little region to such high pressures and temperatures that the oxygen in air dissociates and starts to react. So you can have some air chemistry happening right at that corner that we study in our tunnels. Next, as you flow through here, most of the forebody will become hot because these vehicles are flying at exceptionally high speeds. So frictional drag will make the wall here very hot. What happens to the boundary layer, which is the fluid dynamic layer attached to that wall when you have a hot wall, is also something of interest. Now, why do we care about all this? Why don't we just focus on the combustor? That's what I said I will talk about. As you can see, completely integrated vehicle like this, everything is connected to everything else. So what happens here will affect what happens here, and therefore what happens in the combustor. So it becomes necessary, almost inevitable for us to understand all the little bits and pieces before we can address what's actually happening in the combustor. The next thing we do is looking at the shock interactions. So the shock waves are bouncing around. There's a fluid dynamic boundary layer. There are shock waves. How do they interact with each other? And particularly if you have some hot walls, what happens? That's also something we have studied and continue to study. And the more interesting bit from my perspective and your perspective in the context of this talk is what happens when we put fuel in. How does it mix? Does it auto-ignite? What do you need to make it auto-ignite? How do you hold a flame? How is supersonic combustion occurring in these vehicles? What are the different modes of supersonic combustion? And can we actually look at some of this and see what it looks like? So that's setting the context. Where we do these experiments is in the T4 Stalker tube, which is a free piston driven high enthalpy facility, impulse facility at the University of Queensland, built in the 1980s. Here's a schematic of the T4 Stalker tube. I'm not going to talk about the operational detail of this particular facility. You might have seen it in other AFMC talks by many of my colleagues, but I'm just going to focus on what it can deliver here in the test section. So firstly, there's the video of what it looks like when the T4 shock tunnel fires. I don't have an audio, unfortunately, to go with that. But you can see that there's a big light flash, and it is producing test conditions here in this little test section that are comparable to what's shown in this map. So again, going back to that altitude Mach number sort of reference, which we saw in the first slide, if you look at what T4 can produce, it's this gray image here. Those are the test conditions that the shock tunnel produces. On top of that, I've overlaid a few lines of interest. So what's the total enthalpy? That's something we worry about for scramjet combustors. Is there enough enthalpy? Is there too much enthalpy? And then what is the Reynolds number, which is a fluid mechanic quantity of interest to all regimes, particularly if you want to understand how transition happens and where is the flow turbulent in the vehicle. Now, on top of that, I've also put on some past hypersonic flight experiments just to contextualize and show that this facility, with what it produces in terms of test condition, adequately captures most of the trajectories of or test conditions of past hypersonic flight vehicles. So therefore, it's a ground test facility that produces flight match test conditions, and some of those conditions are shown here in a table, as you can see. Okay, now I promised in the talk, in the abstract, that I'll give you a little bit of history, and I'll do that very briefly here. So firstly, this was the T4 Stalker tube I described, named after Ray Stalker, who is widely regarded as the father of Australian hypersonics. Ray started his academic journey in Canberra at ANU and then moved to UQ. In 1987, as I said, T4 was commissioned in the 80s, was the largest Stalker tube in the world back then. But then over a period of time, this design, because it was so successful in producing ground test conditions that match flight precisely and adequately in terms of test times, even though it's not very long test time, it's enough test time to test with. These sort of enthalpy facilities, high enthalpy facilities, propagated around the world. As you can see, there's a legacy of T4-like Stalker tubes in other universities, T5 at Caltech, T6 at Oxford, and there's many other. I won't go through the whole list there, but you can see that this design has been a very successful design for a ground test facility to produce those kinds of conditions. Now, somewhere along the line, and I'll give you a little bit more history in the next few slides, there was a question around when we started to test scramjets. This was much before I arrived at UQ, of course. and the people who were the original starting point for the Center for Hypersonics started to test scramjet or supersonic combustion models and produce test conditions that seem like this seems to be the technology that works. And in fact, when they first measured net positive thrust in an engine, there was a lot of question and debate internationally on, was this really true? How can you believe what the shock tunnel data shows you? It's for a small amount of time. And there was questions that arose around what we had done. So one of the chief proponents, who is now back at UQ as a professor, research professor, Alan Paul, said, well, I'm going to prove that this is true. So he went about securing partnerships around the world and initiated the High Shot program, which is a UQ initiative, essentially to flight test and demonstrate that what we were seeing in the shock tunnels was indeed true. And so that led to a series of activities in the flight experiment regime. We had the world first data of supersonic combustion that confirmed that what they were seeing in the tunnels in T4 in particular was true in terms of the combustion capability at those speeds. And then this led to other programs down the line, including high costs. And at some point, the international community took notice of all of this and said, well, it looks like we have to do this in a broader scoped sort of program. And it became High Fire, which had several partners around the world and several flights, excitingly enough, over a decade of testing. So here they used two different rocket trajectories, and I'm showing you all the different high fire vehicles that were flown or tested. And many of them, you can see scramjet and axisymmetric scramjet appearing. So many of them had a supersonic combustion sort of test as its basis. So again, just looking at those series of vehicles and flights, I'm concentrating, because in the context of what I'm going to talk to you today about, on supersonic combustion with what kinds of fuels that were being burnt. High Fire 2, which was not led by the University of Queensland, used ethylene. High Fire 3, which was managed by DSTG, used hydrogen. There's a lot of hydrogen testing in different scramjet vehicles' actual flow paths, including in the REST engine, which is a rectangular to elliptical shape transitioning three-dimensional engine. Okay, so coming back to, given that history and where we were with that, and coming back to what we have been doing more recently. So I talked to you about these four different parts in that supersonic combustor that all need to work together to make it work. So briefly, I'm going to touch upon some of what happens in the inlet, what happens with fuel injection mixing, flame holding, supersonic combustion modes, and how that can lead to an unfavorable, undesirable phenomena called unstart. But mostly, like I promised, I will focus on fuel air mixing, flame holding, and the combustion modes. Okay, so before we get to any of that, what is the challenge in front of us? We need to understand the research challenge and what is it that we're trying to conquer before we talk about how we achieved it. So first things first, here's a plot of ignition delay. For those of you who are of a combustion background, you'll be familiar with this chart. This is plotted at about half an atmosphere, which is the kind of pressure we expect after all the compression happens through the inlet isolator and so on, and when the flow arrives at the combustor entry location. So at 50 kPa or half an atmosphere, for these different fuels at different temperatures, these are the ignition time delay in milliseconds. So as expected, hydrogen has the lowest ignition delays. It's a beautiful fuel in terms of combustion. No problems burning hydrogen in almost any vehicle, but all the problems start occurring when you look at hydrocarbon fuels. Now, to contextualize this a little bit more, the speeds at which air is flowing through this vehicle comes in at 2 kilometers a second outside, rushes through, and you can see here, it spends about a millisecond within the entire, from where it enters to where it exits the engine. And now if we narrow down on how much time is it spending on the combustor, which is where we hope to mix fuel and burn, it's a fraction of that time. So that makes the challenge even more difficult. And we can see here the intersection with hydrogen is reasonable. All you need to do is achieve compression of about this temperature at half an atmosphere and it'll burn. Whereas ethylene, still possible, maybe if you compress a bit further, but some of the other hydrocarbon fuels which might be of interest, which are commercial fuels, won't be burning in this engine with this much of residence time in the combustor. So that's a challenge. And how do you overcome that challenge is most of the work we've been trying to do. Now going back to the different segments and what's happening through them. And some of this I'll talk in the context of how we actually don't just focus on the combustor for fuel injection, we might actually inject fuel somewhere else. And so in that context, there is things we do outside of the combustor that helps the combustor. But first things first, just going back to what happened at that four-body leading edge, where you might have a blunt leading edge. This is a special condition, which we hadn't been testing in T4. It was a very recent project sponsored by the Office of Naval Research in the US, where we had test conditions at 10 megajoules per kilogram, which is what you need to simulate what happens around that leading edge tip when you have a big, strong burr shock around there. So we went through a series of test shots development to get back to that test condition of around 10 megajoules or 11 megajoules per kilogram in a recent T4 shot, and then we tested with that. Now we're collaborating with Purdue University on this extensively, trying to understand what happens, how does that shock wobble or oscillate, and how does it produce vorticity. We have made some measurements, and they are providing simulations in support of that. And hopefully this code that they've validated against the experiment will be used in a future vehicle design. So that's why it's rewarding for us to collaborate with groups that are actually doing that kind of work. Coming back to very much the combustion focus, as I promised. So like I said, we focus on the combustor, but we also take advantage of the fact that we have that whole flow path ahead of the combustor. Potentially, we can inject fuel somewhere upstream. We're one of the very few groups that does that. A lot of the other international community that does work in experimental hypersonics, particularly in scramjet research, shy away from injecting fuel up in the inlet because they're worried about what happens if that causes this undesirable phenomena, which I'll talk about at the end, called unstart. So we embrace that as an opportunity, not a negative. So we try to inject fuel upstream. This is a very fundamental study sponsored by a Defense Science Technology Group, where we looked at injecting first with a normal porthole injector, but also use a porous injector along the wall to take advantage of phenomena called boundary layer combustion. The idea there is we can reduce some of the skin friction if you raise the temperature in the boundary layer and lower the density. So you can see here luminosity images, OH-PLIF images, as well as chemiluminescence images. So what happens when you have boundary layer combustion on a standalone basis with just that porous injection? And we also did some testing. This was with hydrogen fuel, I must add. We also put some fuel in the porthole injector and compared how the two things interplay with each other. Again, very fundamental sort of phenomena. You can see here a case where the mainstream injection is on, and there's the porous injection is on, and the two things combine together. Now, this might be a way for us to kickstart some of the ignition and combustion we want before we even arrive at the combustor, where we might inject a lot more fuel. Okay, so that's one thing. The other thing we've been doing, this is my colleague Tristan Vanier's work. He's looking at thermal compression. So you remember you have that inlet that does the compression for you. What if you don't have a symmetric inlet? You have different ramp angles. And what if you try to produce high thermal compression that can lead to ignition, particularly of the fuels that don't want to burn easily? So that's a body of work he's done before. And he's progressing this a little bit further with the new project we now have with the US Air Force, looking to see if we can burn fuel that have a lot more methane content in it, which is a fuel that doesn't burn readily. Okay, so that work's coming online. And if you're interested in reading about the thermal compression concept, I will refer you to this paper is published at Aerospace Science and Technology. Okay, moving further along, through that four-body, we now encounter the inlet where we have hot walls, and then we have to look at what happens through those hot walls. So we have been doing that. To do that, of course, in our transient test facility, which produces test conditions for a couple of milliseconds, we won't get the natural frictional heating you will get if you fly for a few seconds in the atmosphere. To compensate, we actually put electric current and electroresistively heat a graphite plate to a representative temperature. So we can see here we got up to 900 Kelvin, which is pretty hot, in the shock tunnel, and then make some measurements, convince ourselves we're getting those temperatures, remove all the thermocouples, mount the plate, and then do the testing. So here, one phenomena we can see already from the slitted image of those heated flat plates, unheated plate versus a 600 Kelvin heated plate at a Mach 5.5 enthalpy or a Reynolds number of 9 million per meter. We can see that the boundary layer becomes thicker when we have hot walls. And this phenomena is also witnessed when we go to much higher temperatures, around 900 Kelvin, things start becoming turbulent, in fact. Okay, we also did some fundamental measurements. I won't talk in great detail, except for those of you who are interested in high-speed boundary layers, you might be aware that the second mode instability is the dominant instability. We have developed a differential interferometry system that can make measurements of that, again, unheated and heated, and show what happens to that second mode as we go through with the heating process. Now, one thing that happens is, yes, there's a four-body, but then you go through the isolator, there are shock waves inside called the shock train bouncing around, and it is bouncing around on this heated boundary layer. So that naturally triggered a curiosity of, if we see boundary layers becoming thicker, what happens when a shock impinges on that thicker boundary layer compared to a unheated boundary layer? So we did a series of experiments with my student Eric Chang's work, sponsored by National University of Singapore. Again, using that flat plate, we mounted a shock generator and impinged a shock and put it in the field of view here of a Schlieren imaging capability and looked at what happens. So firstly, this is the condition that we were testing, unheated at 300 Kelvin wall. So during our test time of a few milliseconds, the wall doesn't get hot at all. So it's 300 Kelvin at this Reynolds number, 5 million per meter. And then from the visualization, we can see that this is where the shock, when it impinges, creates a separation bubble. That's the extent of the separation bubble, as shown by the red arrow pointing down. Now, as you go to a hotter temperature, so around 500 Kelvin in the next shot, we can see that that separation bubble has moved, has grown, has become larger. And then as we go even hotter to 660 Kelvin, we can see we're now out of the field of view. So this has real implications. So if you have a hot wall and you have designed your engine without consideration of that hot wall, you might have a large separation bubble that might do some fluid dynamic nuisance that you didn't expect and might cause some unstart because of that. So we have to be aware of that and make sure that we don't have laminar boundary layers coming in and we need to trip the boundary layer to make it more robust. Now, alongside that work, we also bid for and got an ARC discovery project that looks at now what happens if you have a side wall. So far we're looking at this as though it's a two-dimensional object. It's not. There are side walls. And so when you have those two shocks interacting and you have hot side walls, what might happen in this complex region where there's a boundary layer that's been stimulated by this heating, and we wanted to have heating that's not uniform, have strip heaters that can produce different effects in the second mode, and look at what happens to that complex region in physics. This is a multi-university collaboration. We've got some world-leading partners as shown in that slide there. And one of the things we are able to contribute because of point measurement techniques. We have 8 different points in space that we can measure at the same instance in the same shot. Now I noticed my internet went unstable. Are you able to hear me now? Yeah, okay. Okay, good. So one thing we are contributing, this is a historic sort of experiment. Many people have done with 2 wedges this shock interaction experiment. But what's new and what we will be contributing that's new is this diagnostic technique that allows us to interrogate not just on the surface with surface sensors, but throughout the flow field, what is happening when you have this complex 3D interaction between 2 shocks and the boundary layer. So that measurement that we are showing here in the purple is we've already done 1 instance of that measurement. I'm not going to show you that in today's talk, but we will be proceeding with that, and hopefully in future AFMC talks you will see our groups work on that, with particularly with these heated strips and with more diagnostics around that region. Other things that we are interested in that sort of link up with this is we saw that patterned heating problem. I saw this in a paper with Johns Hopkins University where they claimed that through their simulations, they demonstrated, I should say not claimed, they actually demonstrated that with an optimal heat flux arrangement on the wall, how you achieve that is a different question, but with an optimal heat flux, you can delay transition. So we bid for a project that wants to demonstrate that experimentally. This might be a way to passively control where transition occurs over the boundary layer. So it's an extra exciting fundamental fluid mechanics problem. We'll have some real applications in this scramjet and or other high-speed vehicles. And my student who's working on this project has done a test trial of this, how to isolate the heat so that we can provide strips of heating that can then manipulate that boundary layer and control where transition happens. Again, I've been stepping away from the main purpose of today's talk, which is coming back to combustion. But like I said, all of this will have an impact. How the boundary layer gets thickened or manipulated through these hot walls and our passive control systems will all feed into our combustor. So in the combustor, we're going to deal with whatever comes from upstream. So it's imperative that we understand what's coming from upstream and use that to our benefit for the combustion process. Okay, so the next thing that we really started to work on, and this is going back to several years of the body of work I've been contributing to experimentally at UQ, is looking at what happens with fuel air mixing and what do we do to get this flame to stabilize inside of the combustor. Now, before I talk to that in great detail, I will talk to the legacy of the work that happened, and I'll motivate why we had to actually step in and do the fundamental work as a second part to the legacy work. So firstly, the legacy work, you saw all those high-fire experiments, which were flight experiments using scramjet vehicles. Many of those scramjets were ground tested in T4. So some examples here is a rectangular to elliptical shape transitioning engine called the REST engine, which was a vehicle that was repeatedly tested in many instances in the tunnel, but also got some flight testing. Here's a Mark 8 version of that being tested by James Turner's work. And essentially what we are showing you here along the length of the vehicles from the side profile, we are plotting normalized pressure, normalized by the first pressure transducer here. And on the body side, which is the top side, the top part shows you the pressure. And on the bottom side, which we call the cowl side, you can see the pressure. And the reason it starts here is that the top side only has the inlet and so on, and the side wall sort of close into a cowl, which I will actually show you a peek view of over here. So the front part of the engine looks like this. You can't see it in this view, but you can appreciate that it's projecting out towards you, and the combustor actually starts downstream of there, and the inlet starts to close down into an elliptical combustor. Okay, so coming back here, so therefore you have the top and the bottom are not identical, they're not symmetric. It's a inherently three-dimensional flow field from the inlet onwards. So we have here options to inject fuel at some locations. And we can see here that there's a fuel injection here in this instance, just on the combustor side. And what you're seeing here are two plots, one where there was no fuel injection. You might wonder, why is the pressure behaving like this? Why is it going up and down? Remember, those shock waves are bouncing around inside of this flow path. So anywhere the shock wave pinches close to the wall, you'll get a spike. If it's away from the wall, there may not be a big spike. So therefore, we get this kind of a pressure profile up and down on the top, on the body side, on the cowl side. And then we claim victory of supersonic combustion having been successful after we inject hydrogen here by comparing it to a case where we have an equivalence ratio of 0.91. Now, equivalence ratio 1.0 means we have injected stoichiometrically. Those of you who are combustion experts will know that that means we put the right amount of fuel, if everything burns perfectly, to burn all of the oxygen in the air. So 0.9 is close to stoichiometric. That's a heavy amount of fueling. And we see here a significant deviation in the pressure profile between the unfueled and the fuel cases. And that led us to believe, and you can see this on the body side and on the cowl side. And that led us to believe that this is supersonic combustion. Okay. Now, I've shown these kinds of plots to many conference audiences, and then invariably I'll get some person put their hand up and say, how do you actually know it's burning? That was a question I had to carry in my heart for many, many years until we could actually answer it. We would point to this and say, look, our error bars, we point error bars on this and say, look, here's a plot with error bars of that same sort of engine now going to Mach 12, which was one of my first students, Will Landsberg's work. Mach 12 is a very high speed, and even with hydrogen fuel, which burns nicely, it's difficult to burn. So we had to inject fuel at the inlet, which is something we, like I said, embrace and take advantage of mixing the fuel from a far upstream location, so that by the time it comes to the combustor, there's already some pre-mixing potential for ignition, and then we inject a lot of fuel here. So this shows you the split between the inlet and the combustor injection of fuel. Again, here there are 4 different curves. Again, normalized plots in pressure, unfueled, a combustion suppressed case, which was our first sort of proof to answer that question. How do you know you're actually burning supersonic combustion? We said, well, we'll inject something that's not going to burn, nitrogen as our injectant. Instead of fuel, we'll inject nitrogen. That's the line in the blue. So when you inject nitrogen, because of just the mass addition, the shock structure changes inside, you see a bit of a bump up in the pressure, but that's not supersonic combustion. However, if you start injecting to much higher equivalence ratios with just a pure fuel, in this case hydrogen, you can see much higher kick up in the pressure, and that's again indicative of supersonic combustion. Here also, people will put their hand up and ask, how do you know it's actually burning? Okay, we'll come to that. How do we know it's actually burning? Now, because we've done so much work with hydrogen fuel, we had a project where people wanted to test with hydrocarbon fuel. And of course, our natural inclination was put in a REST engine and do something in the combustor so that we can avoid this ignition problem with hydrocarbon fuels, potentially put a flame holder in and just try it. This is where I encountered the ever optimistic Aussie saying, just give it a go. And it's a saying I like a lot because it charges me with positive energy, but also one I'm very wary of when somebody says that to me, that they're going to do it and just going to give it a go without having really rationalized everything that goes on underneath. So here's something we tried with ethylene. It didn't matter. When we put in a REST engine, this was my student Zach Denman's work, where again, those kinds of pressure plots, you can see unfueled, the combustion suppressed with nitrogen, which is the square, and then everything else is fueled. You can see a distinctive difference between the pressure profiles between what we don't expect, there's no fuel, what we don't expect to burn and where it's burning. So again, we kept saying this is burning, and people will keep asking that same question again and again. But one thing we didn't realize when we did this, we thought we were very clever. Oh, we're going to make this burn so much better if we just put more fuel in the inlet, right? Because hydrocarbon fuels mix for a longer period and burn much better. We didn't really design those injectors to accommodate for the density differences between hydrogen and hydrocarbon fuels. And we tried a few instances where we chucked some fuel into the inlet, and it didn't really look very different, or it didn't actually burn very well. So that sent us back to the drawing board, and hence my journey to understand what's happening, what is fluid mechanically happening when you try to inject. So then we went into a series of fuel air mixing studies and trying to understand how do you mix the fuel in these vehicles. What is the best way? Is it better to put the fuel in just one injector, or should we have a cascade of injectors back and back that creates a bow shock with the first injector and then punches in with a much higher injection of the second injector that gives a better mixing profile? So we did a series of studies on that. Somewhere along the line, there was interest in injecting fuel at a supercritical state so that it looks like a liquid in density profile, but behaves like a gas instead of having liquid droplets that don't evaporate very well and don't burn very well. So this became a project we undertook and tested in the T4 stalker tube. But again, coming back to what I said, I'm going to talk to you about, which I'm getting to very slowly towards the second half of my talk, supersonic combustion modes. So going back to that image I showed you at the start, which was there is very little airflow residence time to start with, a millisecond, and even smaller amount of time in the combustor. And when you encounter any of the hydrocarbon fuels, you start getting into the difficult, will it burn sort of question. So we need a flame holder. What's a flame holder? Well, it's not this chap holding it in his hand. It's going to be a fluid mechanic artifact that we designed, which people have designed. So this is the shape of a flame holder that you will encounter if you go pick up any supersonic combustion scramjet paper using hydrocarbon fuels. People will put a flame holder in their model and look like this. It's got a 90-degree drop, base wall, and a ramp, all designed so that all the acoustic disturbances in here are inhibited to an extent, and it does its job. So what is it doing? Upstream of this, we inject the fuel. The fuel gets entrained in here. There is a primary vortex and a small secondary vortex. These things are mixing and churning and spinning air and fuel together. There is a boundary layer which becomes a shear layer on top of this. Through that shear layer, we're transporting some of the mixed fuel air into a region where you have high enough thermal compression. And this also becomes very fuel and mixed coming out. And typically the flame holding starts occurring in this corner of this flame holder. Now, when we looked at this, we tried to find, are you able to hear me? Am I stuck? Okay. We tried to find where did this shape come from and who did the first experiment. So my student, Will Landsberg, graduated with his PhD, started working on hydrocarbon fuel systems, found the paper from 1957 where somebody had applied this for a Mach 0.3 combustor. So very low speed. It went through different iterations where people had rectangular cavities for some time. And eventually this sort of relieving the acoustic noise that starts to build up in here was made necessary. It went back to the 1957 shape, stayed there forever. We looked at this and went, we understand this vortex, it's needed for mixing. This is where you increase your residence time, right? So normal residence time, if it's flying through, it's going at this speed, but by slowing it and churning it here, we're dramatically moving this line upwards in terms of the residence time being much higher, and we can then definitely burn some of the other fuels. But do you need this little vortex that's spinning as a secondary thing that comes about, causes drag? We did a series of numerical simulations that removed that shape and changed it to a shape that does not build that secondary vortex. And all our simulations indicated the performance will be similar, if not better, and the drag profile might be actually better. So the question was, we need to test these things. Okay, so how do we test these things? Historically, we've been used to just putting in the full three-dimensional scramjet and testing it. We took a back step from that, particularly when we didn't understand what was going on with the fuel air mixing with hydrocarbon fuels. We said, let's just focus on the part that we need to understand, which is fuel air mixing and combustion. So let's design a combustor that's suited for this purpose. Instead of doing the full three-dimensional complicated inlet, let's choose an axisymmetric simple geometry. So that was this geometry. Now the next question is, when you're not dealing with a full three-dimensional scramjet, how do you guarantee that you achieve the right conditions in the combustor in terms of the pressure you need with the compression? So we thought about this and we decided that this is what we'll do. We're targeting this condition. That's our flight condition. we can use a Mark IV nozzle in the facility. And instead of having the full three-dimensional inlet, we're going to put in an axisymmetric combustor, which will take in flow coming out at Mark IV with the right enthalpies that is equivalent to a Mark 7 or 8 scramjet vehicle. And then because it's been processed here, it's almost like it went through the shock and has arrived here at Mark IV at this station in the real scramjet at the right enthalpy. We're putting that into the model and processing it further to get the combustion to work. So that is in every series of experiments, and I get this question as well. You're testing with Mark IV nozzle, but you're saying it's a scram mode combustor. Yes, because we've made sure that the enthalpy of what's coming here matches what would have happened at this station in a real scramjet. So that's what we're doing. Okay, so we designed this model. This is the second version of that model. The first model was a bit more continuous. We made this a lot more modular, and I'll talk to what each of these little pieces of metal are in a few slides' time. But at the moment, going back to that kind of a chart as I showed here, we now have a diffuser instead of an inlet that compresses the flow, brings it to the right condition in terms of pressure and temperature at the station before we inject the fuel. Then we inject the fuel, we have some kind of a flame holder, and we hope that auto ignition kicks in and burns the fuel, and we get combustion, we can verify combustion. Now, that $1 million question, do you actually burn fuel? We started to want to prove that we can burn it, and the only way to prove this is to do some visualization. Now, all of our model is made of metal. There's no opportunity to visualize. So we decided to do some probing at the exhaust, just at the exhaust plane of that model to see if we can measure any combustion radicals coming out, which will indicate combustion is happening. Okay, so firstly, again, those normalized plots, now normalized by pressure transducer 5, because we didn't want the scale to be too large, because we knew the pressure will mount a bit when we do this experiment. Again, here, unfueled in black, combustion suppressed, that is the nitrogen fuel shot in blue, and then a series of different equivalence ratios, scram mode in green, jet wake anchored mode, and I'll talk about both these combustion modes in just a second, at equivalence ratio of 0.7, and then close to stoichiometric, we see something called dual mode. And you can see the pressure profiles here, unfueled and the combustion suppressed in blue. The green shows definitely higher pressure than the other cases, indicating supersonic combustion, like we've always believed. Then jet wake anchored, it's a higher fuel injection rate. We can see that it kicks up to a much higher pressure around the injection plane in the wake of where we inject the fuel, hence we call it jet wake anchored. And then dual mode, where the combustion is so robust that it's actually caused a separation bubble to propagate, and you see this big sort of pressure profile here. Okay, as I promised, answered that question. So we did PLIF studies, planar laser-induced fluorescence of OH radical, and we looked at the back end. So we put a plane of laser light at the very end of the model, at the exhaust plane of the model, and we started to investigate that at different operating conditions. So flight equivalent Mach numbers ranging here around Mach 7.5 to Mach 8, an actual Mach 8, Mach 9, and across different equivalence ratios. And then we broadly characterized based on the PLIF, we were seeing different combustion modes. And the first combustion mode we could discern from this was scram mode, which had a ring-like OH structure. So a core supersonic flow, a ring-like structure that comes out of the exhaust. Now, OH is a radical that sort of persists for a long time. So it's not a transient radical that is instantaneously consumed at the flame front. It does propagate and stay in the flow. So it's a nice radical to visualize downstream of where the combustion happened. Combustion happened somewhere here potentially and still burning a little bit here, but we can see the OH ring. And we saw this ring-like structure that indicated scram mode. And other instances where we had put too much fuel in, you'd get this isolated blob, which looked like different from scram mode. And so we could characterize what these modes were. Interestingly enough, these experiments were conducted across a 3-year period in 3 different test campaigns with the same sort of model, but nevertheless, 3 different experiments around 3 different years. And when we took the centroid of all of these OH ring-like structures for scram mode and plotted it against equivalence ratio, we saw that it all collapsed on one line. So it was interesting. Scram mode is a very sort of well-characterized mode. And any other mode that is not scram mode sits outside of this line. So it's also an interesting quantitative finding from just a pretty image. Now, coming back to what are these metal pieces? So we said that 1957 flame holder with that shape, we showed through our numerical simulations that you can actually modify that shape and it should be fine. But again, when you come to a design of a vehicle, nobody wants to take these risks if somebody hasn't shown it that it works. So we decided to use our axisymmetric simple test bed model and design multiple modular pieces that will all have different cavity shapes, depths, and so on, so we can test it. So the first thing we did was a simple modification of a 45-degree angle here instead of 90 degrees to get rid of that corner vortex and test that, which we did. And in the next instance, we also changed the depth of the cavity. How deep does the cavity need to be? So firstly, I think I've got these results in the flipped order. So firstly, I'm showing you here results that show you the comparison between a 4 millimeter deep cavity, that is this depth here, and an 8 millimeter deep cavity, scram mode. So if you, again, as always, to disclaimer shots, unfueled, combustion suppressed, and a case where they had no cavity to show that it won't burn. Ethylene will not burn without a cavity, or will not burn very well without a cavity. And then we had the case where we had two different cavities. You can see here the flame holders behave similarly. There's not much to say about any differences. Within the error bars, they're all about the same. They both robustly activate scram mode combustion. We can see that evidence here. And we believe it because we have those ring-like measurements we made of PLIF. For anybody who doesn't want to believe it, I can share PLIF images. Okay, so next, we looked at what it does when you have slightly higher fueling rate, and we can see now a distinct difference. The 4 millimeter cavity was enough, it looks like, to achieve what might have been a jet wake anchored sort of case. However, and even no cavity case starts to ignite and burn because you're injecting so much fuel that it's causing auto ignition. But the 8 millimeter cavity actually makes it go into dual mode. So it transitioned it to a higher combustion mode, which we were not seeking to do. So this might be trouble if you have too deep a cavity. Now, coming back to the shape alteration, we showed through these experiments here, where you have this, the front wall is 90 degrees or 45 degrees. That's the symbol used here. You can see scram mode, there's not much difference. All the other modes that we encounter, jet wake anchored and dual mode, also they all look and behave the same. So modifying the shape really has no performance changes in terms of combustion modes, but we showed through a simulation that you could actually gain a bit of drag reduction by doing that. So it might be advantageous to do it. Now, the next question that got asked to us, challenge that got thrown at us, was conjugate heat transfer that might happen because you have hot walls in a real vehicle. The walls will interact with the fluid. The heat will get conducted through the metal or whatever material you're using here upstream. And then that boundary layer will get even more hotter, even more thicker, and the shocks will bounce off at different angles. What happens then? Damien Curran did these simulations for me when he was a brief postdoc with me. And he showed that at different fueling conditions, you can actually see a distinctive difference in what happens inside. On the top is a 300 Kelvin wall unheated. On the bottom, you allow conjugate heat transfer to happen. You can see a difference. Okay, so we went about trying to construct a combustor that can be heated using inductive heating, using an inductive heating coil that heats just the inside of the combustor. Now, we just wanted to see what was the influence on ignition flame holding. So we only heated the combustor, not the full model from the leading edge. So we were not thickening the boundary layer and all of those effects that will happen. So because of that, when we could achieve hot temperatures as shown here through our experimental demonstration on the benchtop, which we then put in the tunnel, we could see some small differences. So if you heat the model 300 Kelvin versus the hot model for scram mode, you start to see a little bit of pressure oscillations kick up in our plots here. The color is the pressure along the length of the model and the time of testing on the vertical axis. So as we go to the higher sort of combustion modes, you can see a little bit more pronounced activity at higher temperatures, but nothing really that changed the combustion mode or anything. And the reason we believe for that is we didn't heat the front end of the model, which is where a lot of the governing physics would have affected what happens in the combustor. So that is to be done in the future. Now, to further answer this question, are we actually burning? We decided to be a bit brave and make part of the model to be of optically accessible acrylic material, which we put into the axisymmetric combustor, replacing the segment where the combustion happens. We were perfectly happy if this disintegrates and we can't do this and go back to a metallic model. But luckily for us, the first few tests seem to indicate that you can actually get visualization of that OH radical. Now we put UV filters and looking at that combustion, so we can actually see the flame start inside of the combustor, which will be exciting study with that. Alongside this, my student Sarah McClem who's I think on the call, has been doing simulations, and this is a paper she presented at the Australasian Fluid Mechanics Conference, I think 2 years back, where we looked at tandem cavities. Now, instead of a single flame holding cavity, what if you have multiple cavities? And she showed that you can actually get an optimum separation between the cavities that becomes good for higher performance. And the next question was, if we don't want to go to the higher dual mode where the separation bubble sort of propagates upstream, can we inject fuel across the different locations and control that for a longer duration in terms of equivalence ratio? And her work is also quite illustrative on what happens. And maybe there's a way to mix the fuel in a more systematic manner than just dumping it in one location. Now, she did do some brave LES simulations with several million, 100 million cells supported by our DSTG group. And here are some of those results of LES simulations that show you just how that unstart bubble can propagate. If you go to dual mode, you can actually start propagating upstream and unstart. I'll let this play once and move on. But what we witnessed is that our simulations mimic T4's limited test time to an extent. But if we go to the higher equivalence ratios cases, we can get unstart, and that's something we were not able to see in the studies that we did in T4. Now here's a case with the tandem cavities where she's looking at how it works and seems to ignite and burn. Again, we haven't done a lot of experiments with this. That's something in the future if an opportunity arises. But the last segment I want to complete in the 8 minutes or so that I think I have left is to talk about this undesirable, unfavorable phenomena called unstart, which is a showstopper. So I'll talk to you about what unstart is in a minute and explain why that is important. But if you don't understand unstart, it is almost virtually guaranteed that you will encounter this at some point in your operating trajectory and you'll have no solution for what happens. So what is unstart? Remembering that our entire scramjet operates on this shock in the front and the whole shock compression process and fluid mechanics process that happens inside. If you have too much back pressure, that happens because you injected too much fuel, there was a rapid ignition combustion, big back pressure that starts to push upwards. And you could see that in those dual mode plots where the pressure sort of jumps ahead of where the fuel is. And essentially it can go into the isolator, push against the shock train in the isolator, spill that isolator shock train out in the front. And then instead of having a nice oblique shock that compresses, you might actually have a bow shock sitting in front of your vehicle, which means you don't have supersonic flow going in anymore, and you don't have a scramjet combustor. It'll probably drop out of the sky if that happens. So there's lots of groups interested in this work, and hence you see all the names there who are willing to sponsor some of this preliminary work we've done. Now, T4's test time of a few milliseconds was just not adequate to do this testing. We have another tunnel in town, X3R, managed by DSTG, which is we can see the proportions of the shock tube, which is where we keep the air, is much longer in X3R than it is in T4. So therefore, the longer amount of test gas, similar operating principle of the tunnel, we actually have more test time. So about 10 to 15 milliseconds of test time, that's fivefold the test time we get in T4. We were still not sure that is enough test time to see unstart and play with it, but we figured we can give it a go. Again, that optimism of giving it a go. So we tried to take our model and test it there. The problem was they didn't have a Mark IV nozzle, and remembering that we have actually designed this to operate with a Mark IV flow coming in, we didn't have an option of testing option might be to bring our Mark IV nozzle and mount it on their tunnel. And in order to do that, we had to do some engineering innovations around creating an adapter piece that my then student and postdoc Matt Trudgeon designed. And this was a mean engineering activity where you're trying to interface two tunnels with each other. The nozzle from one tunnel goes on the facility end of the other tunnel, which is somewhat difficult to do for those of you who do high-speed testing. All right, so the goal with all of that was, again, this is components designed as the adapter piece that goes on to fit that. And with all of that, our hope and aspiration was, can we test it? And then we had a series of things we wanted to characterize first as operational success. Will it fit? Is everything similar? Will the model line up? Can we get the conditions? And then can we get some results repeatable, and can we achieve unstart? And then if we really get all that, can we go pushing the boundaries a bit further? Okay, so first things first, yes, it did fit. We could put the model in. Yes, there is a nice comparison here of the test time. We get nozzle supply pressure. This is the test time in X3R, much larger than that in T4. So looks promising. Then we gave it a go. Here's a comparison at almost stoichiometric fueling. T4, you'll notice, will stop at 4.5 milliseconds. It's run out of test time completely, and X3R continues, and you can see it becomes horizontal in that normalized plot. What that means is the model unstarted. Okay, so We noticed that, and then we did a series of experiments like we always do, unfueled, different equivalence ratios. Now that we know it's burning inside, when we see the pressurized, we believe it's combustion. And then at equivalence ratios where T4 would have said dual mode, we now started seeing this phenomena where anything that's close to stoichiometric or higher, you start seeing this unstart bubble propagate upwards and spill out and cause a full unstart of the model. Whereas at equivalence ratio of 0.74, you can see it's still sort of attached here. It is dual mode, it's not spilling out. I don't know if honestly, if we have longer test time, if that will spill out, but it looks stable enough at this point that we believe this is like the limit of what the isolator can stop from unstarting. Okay, so now that we got all of that, we made some comparisons. These kinds of plots I've shown you before. These are called our XPD plots with the pressure contours in the color, again, along the length of the model and test time on the two axes. Now this we can only get in X3R. So these are X3R conditions that produce T4-like data, but we can only do this in X3R to get unstart. And once you have unstart, you can actually look at within the unstart, there is also different types of modes that occur. There's a buzzing mode and there's other kind of modes that seems to come about. Now we were unprepared to see unstart, so we didn't even know if unstart will come. But now that unstart came, we started to get a bit greedy along my reasoning of the things we would do. First thing we did was switch off the fuel, see if we can arrest unstart. So we know this case will unstart. We switched off the fuel at a strategic time. And then we could see that red, which is arresting unstart, goes through all the other combustion modes. So it should have unstarted like the brown or the golden, but it didn't. And it goes through all the other modes and sort of stays lit for the duration of this test time. Then we attached two valves to control this fuel timing a little bit so that we had the ability to switch off the fuel through one and activate the fuel through another and time it such that in one case we completely switch off the fuel and then restart with putting in the fuel from the other valve so that they're different in time. And in one case, we sort of manage it simultaneously. One is shutting down, the other is kicking up so that we reduce the fueling. We don't know exactly what equivalence ratio we ended up with, but it was enough to prevent unstart. So the green was a case where it would have unstarted, but because we played this game of reducing the fueling, we could keep it lit. Again, very sort of heuristic ways of doing things. We haven't really done a systematic understanding of the physics of what's actually propagating in the boundary layer. So unstart, again, is an instability that propagates. It will propagate through the subsonic boundary layer. So that's where a lot of the information can be understood and potential to stop it. So we are looking into some of the data here, critical back pressure from literature and looking at when are we hitting the critical back pressure and what do we see. Again, analysis is being undertaken and there's hopefully a future opportunity with a bigger project to do that in. So I'm coming to the end of my talk. So what are the next steps in my view? It's a technology that's being developed by several nations at the moment. There are commercial applications, including a startup company here, Hypersonics Launch Systems in Brisbane. Many challenges exist, particularly around dynamic combustion modes that I showed you today about and leading to unstart and how we control that. And another big challenge, if we have to have sustained scramjet flight, an ongoing and ever-going challenge is the cooling of the hot walls and the materials we use to make this a viable technology. There is uncertainty around dual mode, whether it's a real viable mode. A lot of the performance metrics say operate in dual mode, which means increase your fueling, but it's a risky mode because it can lead to unstart. And last but not the least, I think there's a lot of opportunity in understanding the underlying physics of scramjet unstart. Now that we have these commercial sort of entities coming up, this almost becomes a necessity that we start going into this and understanding and uncovering the physics of how to control this. So I'll stop there and thank my audience for their time.
Thank you so much for the very interesting talk. I certainly learned a lot and enjoyed it very much. Do we have any questions from audience? If anyone would like to ask questions, you can either just speak up or type in the chat. While we wait, I may just ask something. The only part I didn't understand was when you were talking about the test that you did to prevent unstart. So was that with double fuel injection? Okay, so you said
okay, I'll go back to that. This one, so the one you're talking about? Yeah. So we had two valves that we are using to control the fuel that goes into the plenum, right? So in one case, we actuated it such that it shut off the fuel completely So we can see if I play this movie here, I'll let that start playing. Okay, so you can see here a case that where when we did just shut off the fuel, it gets arrested. And then the restart case where we reopen the fuel through another valve and actually goes completely to shut off and then restarts, right? And we didn't have the time to again shut it off to demonstrate that we can bring it back down into a lit case. So this was just showing that if you have multi-valve systems, you can actually control this, and you have a control ID and you know how to control it, and you've got information from the underlying physics-based models, you might be able to develop a reasonable control system that can respond. But the precursors have to be tracked well ahead of time. And again, this is where a lot of the physics we haven't done. I will admit completely freely that we didn't go into this campaign expecting to study that physics in detail because we didn't even know if we'll see the sun start. But that's an opportunity for us to work in the next bit. And this is the case where we didn't do the complete shut off and kick in the fuel in the other valve after a while. We were doing this simultaneously. One valve was shutting down, the other valve was bringing up. So what that means for what's happening to the fuel is instead of the full equivalence ratio, we were effectively lowering the equivalence ratio. And that meant we could prevent unstart from fully occurring. Again, we don't really know what that equivalence ratio is. We can, of course, over a period of time, design something that can measure pressures more rigorously and conclude what that equivalence ratio is and control that more correctly. But all of this we did as an opportunistic sort of by the way experiment in the end, right?
Yeah, no, thank you. We do have one question in the chat from Voisa, who's asking, in dual mode, do we have any two modes coexisting?
So that's an ongoing debate. So my American colleagues believe, when I show them this, they call it the RAM mode. And what they believe is it's not supersonic combustion anymore. It's basically you have a pocket that's subsonic where it's burning, or at some point it has closed completely inside and it has become a subsonic combustion model inside. We, in all our simulations, we have shown that we do have a persistent supersonic core. So, we beg to differ. We call that dual mode. We believe RAM mode occurs in scramjets.
Do we have any other questions, any comments? Okay. I guess then we'll thank you for the talk and end the session here today. And thanks everyone for joining as well.
Thank you.